This is a video on potential energy diagrams. You have on the y-axis chemical potential energy, which I'm underlining right now. On the x-axis, it usually is like the reaction coordinate or something like that. But you essentially want to think of the plateau on the left as the potential energy of the reactants, and the plateau on the right as the potential energy of the products. So potential energy reactants would be, in this particular case, about 10 kilojoules, kilojoules being a unit of energy, whereas the products, as I line this up, have approximately 25 kilojoules of energy. Now the difference between those things is known as the delta H. Delta H is also known as the heat of reaction, so it'll be heat of reaction. It'll also be known as enthalpy of reaction, and it's always the potential energy of the products minus the potential energy of the reactants. And since the products have 25 and the reactants have 10, 25 minus 10 is 15. So in this case, it's 15 kilojoules. Now, since the products have more energy than the reactants, this is an endothermic process. And just to make sure we're clear on this, whenever something's endothermic, that means energy is going in, and anything that's going in is always going to be on the reactant side for reaction. So we'll put the 15 kilojoules in the equation somewhere on the left side of the arrow. It could be here, they could put it over here as well. Either way, it's okay as long as it's on the left-hand side of the arrow. Now, in order to produce product, all right, I'm just going to, let me put the arrow in here. So the delta H is usually an arrow. It's between the two plateaus like that. All right, the rest of the diagram deals with the mechanism or steps in the reaction. And this is the idea that at some point particles of A have to collide to make particles of C. And when they do that, some of their kinetic energy gets converted into potential energy, and they form this thing called an activated complex. So the activated complex would be all the way up here, and this is really arrow number 5 here, kind of going out of order. The activated complex is unstable, okay, and exists, okay, briefly. And we want to keep an eye on this whole, it's a high energy thing. High energy things by definition are pretty much unstable. So it exists briefly, it's high energy, it's unstable, all right, and it really exists over here somewhere at the peak, and it's the product of collisions. Now, since this is a reversible reaction, it can be formed by the collision of A molecules to form it, or the collision of C molecules to form it in the reverse reaction. But in either case, the activated complex has more energy than either the reactants or the products. And so from either direction, so those collisions have to be enough to form that thing. And the amount of energy in those collisions is called the activation energy. Now, if you're starting from the reactant and going to the products, it's called forward activation energy. And the forward activation energy is the difference between the potential energy of the reactants and the activated complex. And so I'm going to put the arrow in here, but really what you want to think about is this. The activated complex is up here at about, I don't know, I'm going to say it's 45 kilojoules. It's not really that accurate, but it's the best I can do on this program. And you could argue it's 40 if you want, and that's reasonable. And so the forward activation energy is going to be the difference between the potential energy of the reactants, which is 10, and the activated complex. So the forward activation energy here would be 35 kilojoules. The reverse activation energy would be from the potential energy of the reactants up to the activated complex, and so that's going from 25 up to 45, and so that's going to be about 20 kilojoules. These 3 arrows I'm going to mark with little stars are the ones that are affected by a catalyst, all right, because catalysts lower activation energy. But we'll talk about that on the other page. A couple of quick side notes here. Make sure you're clear. What this means is for every 2 moles of A, you're going to absorb 15 kilojoules. If let's say if 4 moles of A are going to be consumed, you're going to absorb 30 kilojoules, and so on and so forth. All right. Now, let's talk briefly about what catalysts do. So what a catalyst does is it changes what's called the mechanism of the reaction. That's basically the steps Okay, so in other words, steps of the mechanism. They rarely ask about this on the regents exam. It's really important at higher levels though, because people need to understand how catalysts actually work to speed up reactions. Make sure we're clear. Catalysts speed up both the forward and the reverse reaction because they lower both the forward and reverse activation energy. So they usually draw as a little dashy line like this in between the two plateaus, and you can see the arrow for the forward activation energy is shorter and the arrow for the reverse activation energy is shorter, and the arrow for the activated complex is also going to be shorter. All right. One note about activation energy that kind of throws people I should bring up about this is that the activation energy is also referred to as the energy needed to start a reaction. So if you have to, let's say, strike a match, when you actually strike it, that energy you put in is considered activation energy. If I use a butane lighter to light the Bunsen burner, that's activation energy. So if you put a piece of magnesium ribbon into a Bunsen burner like we did in the lab earlier this year, that's also activation energy. So it can be thought of diagrammatically, but it's also if, let's say, there are no effective collisions and then all of a sudden you make something really hot, you're basically providing the energy to get those collisions to be effective enough to form that activated complex, that unstable intermediate. All right, a quick note about the delta H and the forward and reverse activation energies. The difference between these two is always the delta H. So if you think of it this way, right, I'm just going to make a little circle here, right? This is the delta H right here. Okay, the delta H plus the shorter activation energy always equals the longer activation energy. So the delta H will always be the difference, okay, between these two. So if they ever give you a question and you're missing that information, the difference between forward and reverse activation energy will be the delta H. All right, one last thing. Make sure you can recognize endothermic versus exothermic. So in this case, you have reactants that have more energy than the procs. This process is going to be exothermic. Okay, if we were to do the delta H here, it'd be procs minus reactants, and since the procs have a smaller number, let's say it's like 20, and the reactants have like a larger number, let's say 40, it's going to be 20 minus 40, and so you get like negative 20, let's say kilojoules or something like that. All right, and that, make sure we're okay with it. That goes into the equation as 20. Now note, it's not negative in the equation, but when you refer to the delta H and say, what is delta H? It's negative 20 kilojoules per mole. But in the equation, it's just 20 kilojoules on the right-hand side because it's what's going out, it's what's being released. And a quick reminder, if this were happening in a test tube, it would feel warm, whereas the endothermic process would feel cold. And remember, it's releasing heat. That doesn't mean it's getting colder. It's releasing heat because it's losing potential energy. Okay, quick last couple of things. Note about stability. When things are formed in exothermic processes, if they are at low energy, they are more stable. So we can assume that B is more stable than A because it is the product of an exothermic process. Another quick note, on equilibrium. See how the forward activation energy here is really short and the reverse one is really tall? Okay, what does that mean? Well, if all the molecules are at the same temperature, that means there'll be more effective collisions between A molecules and B molecules because A molecules don't have to collide as fast. They don't need as much activation energy. And this would set up a situation like we saw in the equilibrium lab where, like, let's say the forward reaction was like 60% and the reverse was 20%. When that happened, what we ended up seeing was that when we reached equilibrium, we got a ratio of 3 of these for every 1 of those. So if you see a situation like this where the forward activation energy is lower than the reverse one, chances are the KQ is going to be, like, you're going to have product is going to be greater than reactant. And so your KQ is going to be, greater than 1. All right, that's it. Short and sweet.